our basic reproductive number discussion. And so let us try to calculate or to estimate how many consider one person infected. How many new infections will this person cause during the duration of his infectious period? Okay. So, now, get one person. So, this thing, which will turn out to be R0. Right? Let us just remain with the R0 here and see if this has something to do. Okay? So, so the number of new infections that the primary infectee will create will depend on several things. One of them is the number of contacts a person has. Okay? If you have more contacts, you infect more people. So you will have something which is like some K, number of contacts. Okay? So this is typically this can be a possible infectious concept. So this can be direct contacts, or also sexual intercourse, can be many things. Okay, but there's a certain number. Okay, and so the number of new infections created by one person depend on how many persons the person will meet, and then there must be some probability that this meeting will generate a new infection. But not all meetings, not all contacts will generate infections. So first thing is the person that is the contact of the person that is infected has to be susceptible. Okay? Therefore, the probability that the infection will that the infection will occur given a contact will be proportional to the number of susceptibles in the population, which we use in the same notation, times n, which is this is the probability that the person is infectious. It's just the proportion of susceptibles in the population. Okay? So, but then there's also the number of contacts, the probability that the person is susceptible, and then there should be some other constant, which is the probability that one infectious person will have a certain number of contacts per time, then the probability that the person is susceptible, and the probability that given this encounter, you will have actual transmission, which is a certain probability. Call it P. Okay? So, but then there's something else. I'm not trying to calculate the number of new infected persons from a given initial infectee as a function of time. I want to know, given one person infected, how many people this person will infect over the course of the infectious period of that person. Therefore, the longer the infectious period, the number of transmissions can be proportional to the time the person stays infectious. So there will be a time typical for the infectious person to during the course of the disease. The longer the disease, obviously we are considering no treatment here. Okay? The longer the disease, the more people the person will infect. Okay? So now, this is already something that looks like this, because this is, well, we have just 0 over n. Then you have k times p, which we will call beta. And t is this time here is the typical time the infection, a person stays infected, and this was 1/a in the equations. Therefore, this is actually this, which is R0. Yeah, the mic.
Is that probability P that you called probability of transmission exactly the transmissibility as they define it, or not exactly?
Transmissibility is usually beta. Yeah, so
Beta?
Beta, yeah.
The transmissibility is beta.
Yeah.
Is not inside of beta, because I thought beta took into consideration transmissibility
and susceptibility.
And yes.
Yeah, this depends on whom you talk.
On the
If it's
model.
an epidemiologist, usually will say transmissibility is susceptibility beta. Transmission depends on susceptibility and transmissibility, but more mathematical things, they have just the beta and don't care what is inside the beta. Okay?
Okay.
So here we, in order to come to the conclusion that R0 is the number of secondary infections a given person creates, we had to resort to these things. Okay? But I mean, you could stay from the beginning only with the beta. Okay? This is for the interpretation. Okay? No?
Thank you.
So this gives you the interpretation, and which is coherent. If one person is able to infect more than one, then you have a kind of geometrical series. Okay? If one person infects more than one, then you say you have one person, then you have two persons, then you have 4 persons, then you have 8 persons, and so on. Right? Obviously, you could raise your hand and say, but people, there's a lot of variability. And yes, it's a lot of variability, and actually, this kind of discussion has to take into account that there are maybe k, the number of contacts should be given by a distribution of contacts. There are people that have more contacts and there are people that don't have. When is this important? To take into account that k actually is not constant. It's depends on each person. Therefore, you have a distribution of k's. Well, for instance, this is not very important for measles or the kind of thing that we describe with SIR. Okay, so for instance, it is very important. For instance, in sexually transmitted diseases, for instance, because you can have, I mean, there are persons in the society that have enormous amount of contacts, and people, the distribution of sexual contacts depends on where you look. You can look for instance, in the general population, or you could also separate, is it heterosexual intercourse, or is this men that have sex with men, or women that have sex with women? You can separate. Then you have distributions, and then there are in the society distribution usually have of contacts for this kind of thing. It's usually here everybody's like 1, 2, 3 over a certain time, say 1 year. And this decreases and then goes up. Okay? So there are more people that have 1, 2, or 3 sexual contacts. Sexual contact. In this case, this distribution is actually for different persons. Okay? The partner distribution. 1 or 2 or 3. That is a partner distribution.
But in the case of COVID, for example, I can imagine that you had a really specific set of people who were negationists, and probably these people had more contacts than people who were taking the epidemic seriously and staying at home. So you could argue that K could be a distribution on that case too, as well. Then
the point is how, for instance, the number of contacts, let's say it's like 6. How spread is it? I mean, if it's very a small number of people that are not avoiding contacts and so on, then maybe the effect will not be so big. Okay? This is the point. So everything is, how relevant is this? Because then we will discuss next time. Knowing these are zero and knowing the number of infected and susceptible is very, very difficult in real world. Okay? So this will be on Friday. But just to mention this, so K should be actually a distribution. And this is related, this is important for sexually transmitted disease. In particular, it seems to be very important for monkeypox. Why? Because there's this thing that was kind of mystery, which was, why does monkeypox spread mainly in men that have sex with men, given that it is transmissible to women or to men that don't have sex with men? Okay? It is transmissible through contact. So one hypothesis is that there is a data set from UK, that's the only data set I know, of the number of partners people have. And the number of partners depends if you are a man that has sex with men or a woman that has sex with women, or if you are heterosexual. So this dependence is that this distribution has different characteristics. When men that have sex with men have this kind of here, it's not an exponential decay, it's a polynomial decay. So it's a kind of what does it mean? There are many people that have many. I mean, relatively many in respect to the population here. Okay? There's a part of this population that had like 50 contacts per year, 50 partners, while most of people have one. Okay? But there is this kind of thing. And in the heterosexual population, the proportion of people that are on this part here is much smaller. Okay? And when you try to use these distributions into the models, it will turn out that the transmissibility will depend on your this is inside the transmissibility. It will depend on the form of your distribution of contacts, of partners. And it turns out that one reason people think that the epidemic stayed essentially in men that have sex with men is that this part of the distribution is different for these people. Okay? So, which is more or less, I mean, so then you're going to say, okay, so what does it mean for the public health thing? So it would mean the following. You have to have less sex. Since the beginning of the ages, trying to make people avoid diseases through diminishing or saying don't have sex has not worked in any situation. Okay? So, at least, I mean, you can have a diminution of the number of sexual encounters for a given time. So that is possible. And actually, that happened with monkeypox. And then, of course, most of these heavy tail of the is related to events of parties and so on. And have less parties, you have less. Yeah. And then, what this is interesting, is that the kind of this epidemic did not spread to all population of the men that have sex with men. No, it stayed in a small portion. It is essentially a property of the network of contacts, which has a certain topology, a certain aspect, where these people that have much more contacts than these other people, they mainly contact between them. So they can form a nucleus, and the epidemic stays in the nucleus, doesn't spread necessarily to all the population. Okay? So this is a tentative explanation of why was it restricted to men that have sex with men, and why, well, it was very frightening for all. Why did it kind of decay so quickly? So why is it disappearing naturally? Because and one idea is it's on the ideas market is connected to the network of contacts. Okay. Now, so let us do something else. Now, here, usually when you have a population that has no immunity to a new emergent or new arrival of a new pathogen, S0 is just equal to n, and therefore it's beta over A. But, well, maybe you have a population that has had no contact with the disease, but there exists a vaccine for the disease. But this is the case of measles, for instance. Okay? And most of people nowadays don't have measles. So you don't have natural immunity, but you can get a very efficient jab and get immunity. Okay? So, for instance, this is this case, and then there's also the case which is being seen as a very important threat nowadays, which is the re-emergence of polio, which is was almost how to say eliminated. No, that's better for it's there's a more technical word. Eradicated? Eradicated, yeah. Was almost eradicated. Almost eradicated. But due to the lowering of the coverage of people with vaccines, you can trigger new polio cases. I mean, this is quite complicated because there's wild polio and there is vaccine-induced polio and so on. I mean, there are many aspects. But, well, now, so, therefore, we could say that S0 maybe is not equal to n. When I vaccinate, I just have a certain part of the population which is vaccinated, okay? And then it is not susceptible anymore, okay? So let me write this, put a V here. It's the same as 0, but it's thought to be, okay, that is the number of people that have been vaccinated, and V over n is the fraction of people that have been vaccinated in a population. So now, we want to know how many people I have to vaccinate, okay, in order to in order to lower R0 below 1. Okay, so the threshold value of R0 is 1. Okay, so then you would say R0 equal to 1 is the threshold, okay, which is equal to beta over A times the number of vaccinated divided by n. Okay, so then let me see. Sorry, I made a mistake. It's one. I made a mistake. S0 is not. Sorry. So the number of initially susceptible people, okay, the population initially is S plus V equal to n. Okay? So the initial susceptible people is n minus V. Okay? It's n minus V. Yeah. Okay? Sorry. Okay? So this is the number of susceptibles. Okay? So now the threshold value R equal to 1 is equal to beta over A. Let's see, by vaccination, let's call it only R, because R0 is the totally pristine, totally susceptible population. Okay? So beta over A, 1 minus V over N. Therefore, if I want this to be equal to 1, I have 1 A over B is equal to 1 minus V over N, which implies that V over N is equal to 1 minus A over beta. And A over beta is the R0, properly speaking, if the total population is susceptible, which is, therefore means that V over N is equal to 1 minus 1 over R0. That's the minimum coverage of a population to be vaccinated in order to lower R0 below 1, and therefore the pathogen cannot invade this population, will not have an epidemic. And that's called the herd immunity threshold. And this has been used in very, very wrong ways during COVID, lots of things. And it is defined, well defined, in the context of vaccinating a population. Other things related to this have been made. There were a lot of confusion at a certain moment of time with COVID. So that's connected to vaccination. Now, for instance, if COVID had R0 equal to 2.5, which was at a certain point was something reasonable, this will give you V over N equal to 0.6. Population has to be vaccinated in order to have herd immunity. And there are obviously practical implications that this is not taken into account, but that the vaccines have some efficiency. Okay? Here, this is a totally efficient vaccine. If it's not completely efficient, then you would have that you still have a factor here which will take into account that not all vaccines are efficient. And this is also a case which I am discussing of a situation where the vaccinated never gets infected, in the sense that has perfect immunity without decaying in time. Okay? So this is, therefore, I mean, this is, you have to pay attention not to apply this to real world situations where these other effects can be important. But you can, for instance, polio and measles, they are very efficient vaccines, and then you can actually use this kind of concept. And the point is, if, for instance, measles has I said R0 like 17, but to make the calculation easier, let's say R0 is equal to 20. This means vaccination coverage minimum in order to avoid an epidemic of measles is 95% of the population. And for polio and so on, it's also on this order. So these are big numbers. And sometimes I would say too big numbers. Okay? So in order to achieve herd immunity in a population against measles, for instance, you need 95% coverages, and you have to maintain this. So we had measles epidemics in the world over the last 4 or 5 years. With COVID, this got a little bit masked because people had less contacts, which has also an effect not only on COVID transmission, but also on other closure of schools, for instance, is important for childhood diseases. But in 2018, but I can't remember if 2018 and 2017 or 2018, 2019. I think 17 and 18, we had a considerable epidemic of measles in the region of Manaus in the Amazonas. And this, at the time, had been blamed at influx of people from Venezuela, refugees. But actually, this is a kind of nonsense, because it was not only these people that got the infection. There were other people. They were not vaccinated, the local residents. And therefore, I mean, you can say that the introduction can come from abroad, from any place. But sometimes you have also situations where there is still some virus in the environment, and you need to be protected, even if there's no introduction from outside. One case is yellow fever. Yellow fever is a zoonotic thing, and can there's the usually transmitted by Aedes aegypti, and it stays in the environment. So we don't have epidemics in humans for two reasons. First, we don't have so many mosquitoes in cities. Okay? But second, we are immune usually because it's a very efficient vaccine for yellow fever. Right? So vaccination coverage is very important to maintain herd immunity of populations, and it is, yes, for something which is very transmissible, very high coverage is needed, very high, which means that, for instance, you have to be able to vaccinate all ages, which is difficult. Okay? You have to have a vaccine, for instance, in populations like in Brazil, we have a considerable part of our population is of child. So not every vaccine can be applied can be given to childs, but they are still part of the susceptible pool anyhow. So therefore you see that there are real difficulties sometimes with even having good vaccines and so on to achieve actually the coverage that you would need. Okay? But well, it is a success, a very important victory of humans on pathogens that actually we could diminish very strongly the number of cases of measles and polio, which used to be a frightening disease. It was common back in the middle of the 20th century, but common. And well, even not having achieved eradication, we have not achieved eradication. We have only achieved eradication of one disease in the whole world. You know which one? It's smallpox. Okay? Smallpox, variole. And this one has one thing that helps a lot, which is it is specialized in humans. Only humans have this. In fact, the problem, for instance, you say, I want to eradicate yellow fever, to a point that I don't even need the vaccine anymore, which is the case for smallpox. We don't vaccinate since 1990, I think. People are not anymore vaccinated against smallpox. But for yellow fever, that would be impossible because there are animal reservoirs. If you have animal reservoirs, you never can actually go to the level of eradication. You have control and elimination from the human population, but you need the vaccines and you need to maintain immunity because the pathogen still exists in the environment. Okay? So polio was expected actually to be maybe the next one. And well, it was only remain wild polio. So polio has a property that it's like this. You have the wild virus, but also actually vaccines, or at least a certain class of vaccines, is based on attenuated viruses. They get back into the environment, and then there can be some cases of people getting polio from this attenuated. People that have low immunity, or people that, so there are cases that are vaccine-induced cases of polio. Okay? Most of them are mild because, but means, well, that there is a case. Okay? So the eradication of the wild type had been almost achieved. There were some 2 or 3 countries, I think Sudan and Chad or something like that, where you had still some cases, and you were expecting that with the World Health Organization you could get to 0 cases, and no, then there re-emerged cases in other regions, and apparently due to anti-vax campaigning. People don't take the vaccine, and then they are susceptible, and the virus still exists. Right? It's not eliminated. So only we think that we have eradicated until now is smallpox. And then we had to stop vaccinating. Why? Because there is no such thing as a completely 100% safe vaccine. Always you have to have a cost effectiveness calculation with the vaccines. So any vaccine can have effects that can induce, for instance, a disease, or there are risks. The risks have to be very low, otherwise the vaccine is not even deployed. But if you don't have anymore the pathogen, then it's better stop vaccinating, because you will kill 100 persons per year maybe, but you are killing people. You have only the side effects. The big effect is not anymore there because there's no virus. Right? So this is one aspect of vaccination which is very important. So now let me go back to the presentation, and let's do some more math. Do you have any questions or comments from this part? Let me see where. Okay. So just for you to have an idea, the epidemic curves, epidemic curves for SIR model look like this. Here, come on. Oh, okay, there's a problem with this. So here it is. This is the number of susceptibles, and this is the number of infectious people that go up and down. This is in a boarding school in England, long time ago. So it's really a closed system with very few heterogeneities. So that's why this situation was pretty much well explained by it's a flu. Okay? So And another thing that is you can see with the SIR model is that not everybody at the end will be will have been infected. So how will we see this? Let's again write the equations. We have GSDT. Now, I will do a mathematical trick that is allowed, because these are well-defined functions and so on. I will divide equation 1 per the equation 2. Okay? If I do this, I would have ds dt divided by dr dt. This would be equal to minus r times s times e divided by a times e, which you can cancel. Okay? So, this is, and I will come back to, no, that's it. Okay. And this is dsdr. We can cancel the dt's. And dsdr will be minus r over a and times s. Okay? So, r over a is what? It's the r0. Yes? But here, it is multiplied. So this would be, if you want, minus beta over a times s over n. Okay? But now we are not at the initial point. Okay? We are not at the initial phase of the epidemic. So s here is a function of time. So this we will call this guy here r of t. Because at t equal to 0, it is beta over a, which is r0. And I multiply by the proportion of susceptibles. Okay? And I call this r of t. Okay? So, well, then I need this back. And then, obviously, this is an equation which says gs. Okay, r of, that's a mess. Okay. This r is not the same r. Let's say, I would put a 2 bar. This is the reproductive number, okay? It's not the recovered number. You should have paid more attention. So dsgr is equal to minus beta, is equal to minus r, the r of the reproductive number, okay. I want to go, no, I didn't, better limit. It's minus beta over a s over n. Better leave it this way, okay? So in order to avoid this confusion with the notation, okay? So this is a linear equation for s, okay? Which can be solved. And we'll get s is equal to some s0 times e to minus beta over a times s over n, okay? And times r over n. Okay? So, in infinite time, at the end of an epidemic, the end of an epidemic is the moment the number of infected people is 0. Therefore, the total population is composed only on susceptibles and recovered. Okay? So, being only susceptibles and recovered means that S plus R is equal to n. Okay? So now, at time infinity, okay? After infinite time, we have no infected. Okay? It is obviously not only infinite usually, okay? But mathematically it's only 0 at infinite time. But it's so small that it represents much before infinity. So therefore I can now write S will be n minus R is equal to S0 e to beta over A times times R over n. So this is an equation for R. Yes? It's a transcendental equation. Okay? You have to solve it graphically or numerically. Okay? So this says that you are able to obtain the number of persons that is recovered at the end of the epidemic. At the end of the epidemic, there are no infectious people, and R has no reason to be equal to n. Actually, R equal to n is not a solution. Okay? And R equal to n is not a solution. So, therefore, at the end of the epidemic, if R recovered is not equal to the total population, there remains a certain fraction of the population which is still susceptible, therefore didn't have the disease. Therefore, the disease does not infect everybody. Okay? So R infinity, which can be calculated for more complex and more complicated systems, is called the final size of the epidemic. So there's a famous plot of R in terms of the basic reproductive number, because you see the beta over A is R0, okay? So it depends on R0 in the solution. So R infinity against the basic reproductive number is something that, well, here you have to have 1, and this goes up to n, okay? So I will better plot R over n, which gives you the maximum proportion is 1. So this increases with R, and it has this kind of plot. Well, then you could say, if this is, for instance, like here it's maybe 2, then it will be like 50% of the population. 3, you get 60% of the population. But this increases very fast with R0. Therefore, if you have already something with population with 5, you are at 90% here. Okay, so that's that. Of the population that has had the disease. Okay, so that number you can only be recovered if you had the disease, obviously. So this is a relation which is important, and there has been a lot of discussions with COVID, which overlooked the fact that what you can show, and maybe we can discuss, that what we call the herd immunity threshold, which was 1 minus 1 over R0. It's also the point of the epidemic curve where you have where start to decrease the epidemic. And many people said when we get to herd immunity, we can, okay, it's going away, just relax. This overlooks the fact that herd immunity threshold is much smaller than the final size of the epidemic. And the final size of the epidemic is there is a phenomenon, if you want, it's called kind of overshooting, okay? That the final size of an epidemic is I mentioned it, COVID, it's more like 85%, I said 60, it's 85%. So you have the final size of the epidemic, which means that even if you are decreasing the number of new infected persons, you're still accumulating diseases, and you have high number of people that will get infected at the end. Okay? So this is also an important concept that shows, for one side, that a simple model that R infinity is different from n, from total population. Therefore, they are susceptible of remaining. On the other side, this kind of curve shows that for anything with our basic reproductive number like over 5, this is already very close to over 90% of the population getting infected, which is the way the first estimatives for the potential of COVID spreading and the number of people that could potentially die was estimated in the early part, like in February or March 2020. And this has been a matter of heated debate, because obviously what you need in order to know the final size of the epidemic is R0. And then the number of people that will die will be a proportion of the number of people being infected. If you didn't have so many cases, actually you don't have enough statistics to calculate the proportion of person dying with respect to the person being infected. And moreover, you have asymptomatic cases also, which is also difficult to take into account. But, well, the first calculations use this concept of final size of the epidemic for COVID. In US, this would be a kind of 2 million dead. So people at the point say that this is just panic, it's not correct, and so on. But actually, well, one of the assumptions of this kind of thing is that you will make no interventions, okay? That's the final size of the epidemic if you leave the epidemic going on. Obviously, any public health management would try to reduce the final size of the epidemic. So this is the maximum, the potential of and this 2 million, which it's calculated with a much better model and so on, but 2 million actually is not so far from what's happening. They are almost at 1 million in US. So of that. So it was not that bad actually. And this is because there had been many there have been vaccines, there have been social distancing, there have been contact tracing, and all of this trying to lower R0. And still, it is a number that is pretty much high. So, as the final size of the epidemic depends only on the equation of a beta over A, this which is the basic reproductive number. There is one point that would be nice is if we could calculate the basic reproductive number. So that's the final discussion. We will stop earlier today. But so this poses a problem. How can I actually calculate the basic reproductive number. So from data, I have an initial phase, and I want to calculate R0. I want to know the potential. It's different to have R0 equal to 2 or equal to 5 because the final size of the epidemic will be different. Okay? So you have any idea how to calculate R0 if you have the initial data from an epidemic? Hmm? Yeah, from data.
Like you mentioned, it's usually approximated by the how many people one infected individual can infect. That's
Yeah,
but you need
how do you know? How many
without contact tracing.
how,
It's
how
hard.
do you know?
Yeah.
I mean, you have a person, right? Oops, I'm symptoms. Okay, how many people has he already infected? Say you could actually isolate it. Okay, but it's not feasible on the population. But could try to do this if you have a very low number of cases. But still, there's an asymptomatic phase where he probably infected other people, but he has no idea. Okay, so no idea, and this is. There have been some calculation using this kind of thing at the very beginning in China with populations that were kind of closed and could be monitored and then they had actually, you have to monitor, for instance, transmission at homes and so on, but that's a kind of population with 100 persons and so on, so which gives an initial estimate, and yeah, but usually the point is without having the settings, it is very different. You could say, okay, I just have my model. I plug in the data in the model, and in order to adjust the model, I will find the value of R0 that gives the best fit to the model. Okay, problem. Do I know S in a population? At the very beginning, you can say it's N, but then you want to, okay, I've already initiated it. So, do you know I? No. The number of people infected, think now. What's the number of people that are infectious now? You don't know it. Many of them are infections and they don't know it. So, no way of having I. And no way of having the removed, because there are mild cases which do not go to the public service of notifications. So you are in a bad problem here. You have a beautiful system of equations which explains many things related to epidemics, but when it comes to data, these functions are not the functions that you can measure. So what can you measure? It's usually the new number of cases per day which are reported. Okay? So that's what you see in TV with COVID. Okay? The number of new cases. Now, for COVID, there's a particular situation, which is it's an ongoing epidemic. Because you could say, okay, let's look for an old epidemic. Okay? Then you have all the data is already consolidated, okay? And then you do the analysis that you want to do with it. But if it's an ongoing thing, your data is limited by the way that you collect the data, which takes time, okay? So the number of new cases reported today is not the number of new cases today. It's the number of cases from some time earlier, which have had first symptoms sometime earlier and were reported only today. So there is this delay in reporting. Why should we not use the day of reporting? Because it's an administrative fact which has nothing to do with the epidemic. Depends on your public health services. Depends if you have holidays or not. How many people you have to work on the reporting and so on. So it's not an epidemic fact. So when you have a case, you should associate it with something which would be epidemiologically relevant, which in the best case would be the day the person got infected. But as there is an incubation period, you don't know the day the person got infected because the period's not fixed, it's a distribution. So, but you know the date of the first symptoms. Usually this is more precise. So you should therefore report the cases in connection to the day of first symptoms. So, but I get, when you go to the database, you will get, usually people, how many cases were reported today. But knowing that this you may go back by a statistical method and try to now actually how many known delays of reporting, okay? And knowing the dynamics of the disease, you may be able to estimate statistically the number of new cases today with respect to the date of first symptoms. So you can kind of estimate this. Who developed this here in Brazil for COVID? Actually, it's for Paulo. And so then there is the problem. Obviously, you have to work with this equations in order to somehow get a connection with the data. The data is number of new cases reported. There's underreporting. There are asymptomatic cases. Underreporting is cases that are cases and are not reported because the system is not perfect. And then you have asymptomatic cases, which a little bit different from underreported because the person doesn't even know it. And then he has the situation right now where people know it, but it's not reported because there's no system that easily helps you to communicate that you have COVID. Many of, I mean, I had COVID, many people had COVID, Paulo had COVID, and in 2022, you go, you have this self-testing thing, you say, oh, I have COVID. But then you want to report this, you have to go and queue by the public health station, but then you are infecting people. Okay? So there should be an online way, easy to report it. It doesn't exist in Brazil. In other, for instance, in UK, which has a very long tradition in epidemiology, field data, it's very easy. It's just a barcode. And there's a barcode, and then you say yes or no. You can say, I made a test, and it gives me positive or negative. And very easy to do. And also in Germany, it's very easy. So actually, so there's this reporting problem. So you see that we have nice little models which allow us to understand the patterns of epidemics that you expect and to give you a general knowledge of the dynamics. However, the connection to epidemiological data can be made only if your model is adapted to the nature of the epidemiological data. For instance, in Brazil for COVID, the best data about COVID are number of new hospitalizations per day. Therefore, you will have to modify your model. And instead of S, I, and R, have also hospitalization, people in hospitals. So you would have to rebuild a model which would have the people in the hospitals, which And then you would have to estimate the mortality due to COVID for people that are in hospitals. Okay? So this is pretty much much more complicated. Maybe next class or the last class, I can show you the kind of models that are actually used by people with COVID-19. The models that our group built and others, and that they are super complicated and have a lot of new elements in the model. So, for instance, this is not age structured. So the transmissibility is not depending on age here. Okay? So you could have age. Then you would have to say the susceptibles, which are, say, young susceptibles, adult susceptibles, elderly susceptibles are infected, and so on. And all your rates, recovery time, transmission severity, could depend on the age classes. This is, which is also being a fact for it and for many diseases. So, okay, I think for today that's what I had to present, but we are open to questions if you have some questions or comments about models in epidemiology and blah, blah, blah. So at least one question, then we can have lunch. So we need one. Come on, somebody has to raise their hand. Yeah, one question. Mike.
Can we create a similar model for non-transmissible diseases?
Non-transmissible diseases are difficult. It's not the kind of model that epidemiology of non-transmissible diseases is actually pretty much connected to statistical analysis, the kind of thing that you have with Paolo and Ogro and Paulina. Statistical analysis, which is trying to establish either correlations or statistical causation theory for variables like obesity, for instance, which I don't know, chocolate consumption. This is the kind of thing that the epidemiologists work when it's non-transmissible. This is, I have not seen this kind of model for non-transmissible diseases, for instance. Right? Because this, yeah.
As far as I understand this, epidemiology is really similar to what we were doing before with population ecology, because you have populations, they interact with each other, they interfere with each other and all that. So what would you say is the main difference between epidemiology and what we were doing before with community ecology?
So about this, I have two things to say. First is, let's say this is mathematical modeling of the epidemiology of infectious diseases. If you go to a typical person in the epidemiology department of the public health school of the University of São Paulo, has no idea about this. Okay? They are field epidemiologists. They will try to determine certain parameters of the disease, and by doing field experiments, or they are people that are involved with social determinants of diseases. So this is the 95% of epidemiology is not modeled in this sense. It's a lot of statistics, lots, because they're public health. There's a lot of public health data. So there's lots of people who use machine learning and so on. But modeling is something that people, for instance, a way to calculate R0 which is not by fitting the models. Maybe I can explain this next time. I mean, no people that I know from the epidemiology community working with COVID, a lot of people, nobody knew this. It's not actually people who calculated actually R0 correctly in Brazil. It's our group, right? Because people from Fiocruz also know how to do it, but they were focused on other things. And then we discussed that with them, and then they say, okay, you calculate this, and we calculate other things. And so this is just to set the right wording for the. This is mathematical modeling of epidemics, which is a part of epidemiology. But if you have a degree in epidemiology, maybe you have never seen it. Okay? Well, this is also a cultural problem, because much more than ecologists, people in epidemiology, which have many of them have background from medicine or nursing, are averse totally to mathematics. And therefore there's a difficulty. But well, what you have here is that processes that are different in ecology and in epidemiology. Here you have closed, the setting is population dynamics. And in this sense, it's very, very similar, right? And it is, for instance, I have a former student of mine that is now doing a PhD in Chicago on diseases and something that's called disease ecology. It's ecological conditionings of epidemics, and he is he has to take classes and the classes of the ecology part, and his work was in epidemiology. I mean, his final work for the evaluation, they actually had classes of epidemiology also, like here. So this is pretty much common, because the idea is that we are talking about populations and the population dynamics. Here it's a dynamics on a closed population which changes between classes, okay? But has some analogy with ecology, but usually ecology, the kind of problem that you are looking to solve is different from the epidemiological. Here, for instance, it was very important just to have the condition for a pathogen to invade a population, okay? Which is an invasibility criterion, which exists in ecology, but many things in ecology are different questions, okay? So the modeling principles are very, very, very similar, and also data analysis is similar, so that's why I told, for instance, Paulo is working always with ecological data, but he was very instrumental in doing the statistical analysis from our group about COVID, because it's the same kind of modeling principles, also in the statistical. So, okay, thank you. We continue with epidemiology on